Okay, so welcome back. Today we're going to talk about circuit noise, and we're going to use a power supply as an example and see what is this noise and what can we do about it. Is it real? Is it fake? And the power supply I'm going to use as an example is something I converted from an ATX, computer ATX power supply. And it happens to generate quite a bit of noise for whatever reason. And we're going to take a look at actually what it generates and is it bad? Do we need to worry about it? And how can we fix it? So here's my power supply. I've got it, it has three separate outputs, 12, 5, and 3.3. And here's ground, and I've got a voltage and current measuring. And what I'm going to do is I'm going to hook up this power supply to my breadboard. And the only thing I've got on my breadboard, as you can see, I've got the two wires from the power supply coming down to the breadboard, and they're going, I've got a 1K resistor across the output, just to give it something to do. And then I've got two wires going over to my scope, and we're going to measure the output of the power supply. Now you can see I'm on DC coupling, so I should see the DC and the AC. And I've got 5 volts per division, so I expect it should go 5, 10, a little bit over. And I've got a times 10 probe, and bandwidth limit is off. So let's just turn on the power supply, feeding a 1K ohm resistor, and see what happens. Wow, okay, so here I've got 0, 5, 10, 12, and look at all this noise. Let me grab that. And you can see I've got peaks that are 5, 10, maybe 10 or 12 volt peaks here. And they're occurring this is 2 microseconds, 2, 4, 6, 8, so maybe 7 microseconds. So it's, 200 or 100 and something K hertz switching frequency. So the question is, what the heck is going on here? Is that good? Is it normal? Well, I can tell you it's not good. If you've got a 12 volt DC and you've got 10 or 12 volt peaks, that's not good. So the question is, where's it coming from? What can we do about it? So now you can see on the scope, on the top trace, I've got here what we're starting out with the 10 or 12 volt peak noise coming out of the power supply. And the bottom is the identical measurement once we have implemented the things we're going to discuss in this video. And you can see it's really very clean. It comes down to about 0.1 volt of noise, as we're going to see. And this is the same DC coupled signal. This is a before and this is after, once we go through and apply some fixes to this. Okay, so the first thing you're going to want to do, and we're not going to talk too much about it in this video, is just to make sure that you've identified the source of your noise, okay? It could be a lot of different things. You may think it's one device. It may be some induced noise from another device. You may have lights in your office that are causing it, that are inducing noise. It could be another piece of equipment. It could be a computer. So just make sure you've identified the source by, you might go through and just turn off everything but the device you think is causing the problem. Now, here I've got, with my power supply turned off, you can see on the scope, there's about a volt or two of peak noise showing up on my scope. I'm wired up on the same circuit. But let me unplug the power supply. Even though it's turned off, I'm going to unplug it, and you can see I've unplugged both wires and it's pretty much gone away. So there's probably some induced noise coming from the ground, from other places in the house, or from other sources that maybe we haven't identified. But just make sure you've turned other things off to see if you can identify exactly where the noise is coming from. Okay, so the next thing we're going to talk about is some things that you might be doing wrong in your measurement that might be making the problem worse in terms of of measuring this noise. Now, the first thing you want to do when you're measuring is, you can see I've got this probe on 10 times. Try setting it to 1 times. It will result in less magnification of any noise. And go here and set this on 1 times. That's step 1. Now, the second thing you need to understand about noise is there are 2 big loops of wire here. So you've got this, from the tip of the probe to the ground, I've made a big loop of wire. And there's also a loop of wire here coming from the power supply, and there's also a loop of wire here. The problem is, if there's electromagnetic fields being generated from equipment, it sends this noise, electromagnetic noise, into the air. You can't see it, but when you've got a loop, it induces a voltage through any loops. So the goal here is to get rid of as many loops as you can. So what you want to do with your probe is, you want to, instead of having this big loop, what I'm going to do is I'm going to remove this ground. It just clamps in. Then I'm going to pull this off, and you probably have, when you got your scope, you got your probes, you've got this low noise device. It's basically a little spring thing to connect between the probe and ground. This connects to the ground terminal. So you just put it on here, and now you have a very, very tiny loop as opposed to this big loop. So then what you can do is you can get rid of these and measure between the probe and ground, and that could help reduce the induced noise you're getting here. Now, another thing you can use is what's called a ferrite core. And this is a ferrite core. Basically, you can buy a big assortment of these iron cores, and you basically put wires inside and snap them closed, and it acts like an inductor for what's called common mode noise. So if you get electromagnetic fields inducing noise into a loop, you can get signals that are identical. Imagine a pulse of voltage coming through both wires that are identical. That's called common modes, the common mode signals. And if you add something like this into the circuit, since you've wrapped these 2 wires together into this core, it's like an inductor that applies to both wires. So it basically is a series inductor for any signals coming in that are common mode. If it's big enough impedance, it will block those signals and drop down the noise. So what we're going to try is we're going to try this. Now basically I've taken one of these and 2 wires and wrapped them about 4 or 5 times and then snapped this closed. And what we're going to do now is we're going to see if we can figure out, exactly what does this do, what are its characteristics, and we're going to do some tests and go into LT-Spice and model it and see if it will actually help us. Okay, so now let's see if we can figure out exactly what the characteristics of this ferrite core are. We suspect it's an inductor, okay? It's got an iron core, and we've wrapped this around 4 or 5 times, both wires. And we want to figure out how much inductance it has so we can kind of model it. We're going to go into LT-Spice and model this and see if we can figure out exactly what it does. So I've got my waveform generator here, and it's feeding a signal in series. I've wrapped the 2 wires together, so it's like a single inductor. And going to here, and I've got a 47 ohm resistor across the output, and then just going back. Now, this signal generator has a 50 ohm output impedance, and I've got a 47 ohm impedance here. So if this has no impedance whatsoever, no effect, then this will be kind of a short circuit, and we'll see about half the voltage generated here, coming out from the output as is generated here. So what we want to do is increase the frequency and see how this responds. And as it gets to be a big impedance, a big series impedance, the voltage across the output will drop. And then we can figure out what the effect is, what the inductance of this device is. So right now I've got 1,000 hertz. This is a 1,000 hertz waveform. And what I want to do is I'm going to increase this, and I'm going to go up to 1 kilohertz, 100 kilohertz. Right, so that's 100 kilohertz, and I'm going to start increasing. Now, again, we're looking at the output, and at this point, this inductance really has no effect. As we vary this down, we can see we'll go down to 90 kilohertz, 80, 70, 60, 50. You can see the magnitude of the output really isn't changing. So let's go and get up to some higher frequencies. Here's 100 kilohertz, 200, 3, 4, 5, 6, 7, 8, 900 kilohertz, 1 megahertz. You can see it's still not really changing. Now let's go to 2 megahertz, and wow, suddenly it dropped. So around 1 megahertz, 2 megahertz, 3, 4, 5, and you can see about 5 megahertz, the output voltage is about half of what it was before, which means this is getting to be a very sizable impedance, okay? So we go to 5 megahertz, 6, 7, 8, 9, 10 megahertz, 11, 12, 13, 14, 15, and you can see about 15 megahertz, which is the highest this goes. It's getting down pretty low. So this has an effect down, at above maybe 1 megahertz, okay? So what we can do is we can bring it to the 50% point where the output is 50% of the input, and that comes out to be about 5 megahertz, okay? And that's this point right here. So what we can do is we can now simulate this in LT-SPICE and see if we can figure out exactly how much inductance does this have and what are the characteristics. Okay, so here we are in LT-SPICE, and I have set up a very simple circuit to simulate our waveform generator, our ferrite core inductance, and our output resistance that we just showed on the bench of 47 ohms. And what I want to do is try and figure out exactly what the inductance value of this is, so we can get a better idea on what its characteristics are and what its impact will be. Now, I've gone ahead and I have given it a estimate of about 5 microhenries. And we'll see that's a pretty good estimate. So what we did previously is we looked at this voltage coming out of the power supply. And here it is, and we had about 2.2 volts, and here we get almost exactly 2.2 volts. Again, this is a 5 megahertz sine wave, 2.5 volts peak, which is 5 volts peak to peak coming out of the function generator, and our 50 ohm output impedance. And the voltage across coming out of the function generator is 2.2 peak, and what we can do is measure the output. Now, what we saw on the bench was about a 0.6 volt output voltage at 5 megahertz. So let's click that. Let me change the color so we can see a little bit better. And there you go. Here's 0.4, 0.8. So it's, again, this is about 0.6 output volts. So it turns out this 5 microhenries is a very, very good estimate of the inductance of this ferrite core. So what does that mean? How is that going to impact the circuit? Well, what we can do is we can scan the impedance of this as we vary the frequency, do a frequency scan, and see what happens to the impedance of this with frequency. Okay, so I've set up a AC analysis simulation. I'm doing a decade, and I'm doing 10 points per decade. I'm starting at 1 hertz and going up to 40 megahertz. So what I will do is I will run that simulation, and you can see I've got 1 hertz, 10, 100, 1K, and up to 40 megahertz. So what we want to do is we want to measure the impedance of this as we scan the frequency. So I will do a control click to get the voltage, and that is the voltage across this inductor with frequency. Let me change this to linear so we can get volts. So you can see it's basically 0 volts up to over 100 kilohertz or more. Then you start to build up voltage across this inductor, and ultimately goes up to about 2.5 volts, which is the maximum coming out of the power supply. So the impedance of this way overrides this 47 ohms. So what actually is the impedance? Well, we've got the voltage here. What I can do is I can click on this. I can hit a /I parentheses L1, and that will give us the impedance, or in ohms, of this inductance. And you can see it goes from 0 ohms, and when you get up around 1 megahertz, you can see, remember, the voltage started dropping past 1 megahertz, and we can see it maybe 10 megahertz, you're up to about 300 ohms at 10 megahertz, and up at 20 megahertz, you're around 600 ohms. So over 1 megahertz, this is actually giving us quite a bit of impedance, just this ferrite core device. So you can see it does impact at high frequencies. It can impact the frequency that you let through. Up in the tens of megahertz, you're going to block a significant amount of common mode voltage trying to get through this choke. Okay, so now what I've done is I've wired in our ferrite core between the power supply and my breadboard. And again, I've used a low noise attachment on the probe, and I've set it on 1 times. And you recall previously when we started out, we had like a 10 or 12 volt peak noise coming out of this power supply. So let's see what we got now that we have the ferrite core. Let me turn it on. I've got 2 volts per division. So you can see now we're down to about, this says about 3 volts peak. So we've gone from 12 volts, let me grab that. We've gone from 10 or 12 volts down to about a 3 volt peak. So we've done quite a bit just by adding this iron core. So what that tells us is there was probably a significant amount of common mode noise coming through these wires onto the circuit, and this was successful in blocking the noise. And it also tells us, if you look at this, this is in megahertz, this noise. So it did a good job of knocking down some of the common mode noise at the very high frequencies. So now what else can we try? Well, anytime you're going to do filtering, you're probably going to think about adding capacitors. So what we'll do is we will add a couple of capacitors and see if they have any impact. So let's go back to this. What I'm going to do is I'm going to take a 330 microfarad electrolytic capacitor, and I'm going to connect it to this supply right here and see if it makes any difference. Wow, that made a big difference. Okay, we're 2 volts per division, so let's crank that down to 1 volt. And now we're down to 0.2 volts. So let's take a closer look at that. Let's get to, now we're down to 0.1 volt. Let's grab that. And you can see we're 100 millivolts per division, and we're about 168 millivolts, so 0.17 volts. We went from about 10 or 12 volts down to 0.17 by doing the ferrite core and the probe and also this capacitor. Now I'm going to take another 100 nanofarad capacitor, and see if that helps. So we'll plug that in here. And you can see it does help a bit. With the capacitors, of course, capacitors have series resistance and inductance, and you really have to play around with the right combination of capacitors, and that's a whole different discussion. But you can try some different capacitors, but you can see we went from 12 volts, 10 or 12 volt peaks down to about 0.12 volt peaks. So we've done a whole lot of filtering and getting rid of the noise just by these few simple measures. Now again, it depends on your circuit and your equipment and the frequencies and everything, but this is the kind of approach you might want to take and the different tools you might want to use to try to fix this. So hope this helps. Take care and have a really good day. Thanks.